So once again, hello and welcome everyone to this Timescale AI webinar on the topic of advanced RAG techniques, LlamaIndex. I'm your host, 𝗥𝗲𝗹𝗲𝘃 𝗧. I'm the AI lead at Timescale. I'm not going to be doing the talking today. Thankfully, we have the VP of DevRel at LlamaIndex, Laurie Voss, joining us to talk about advanced RAG techniques. We should be in for an hour of great learning with Laurie.
So, hello everybody. My name is Laurie. I'm the VP of Developer Relations at LlamaIndex. I have been a developer for 27 years now. Before that, I co-founded a couple of companies, including NPM Inc. But these days, instead of talking about JavaScript, I'm talking about AI. What are we going to be talking about today? We're going to recap Retrieval-Augmented Generation very briefly. What is it? Why do we do it? What are the challenges? How do we do it? And then we're going to go into LlamaIndex and how it helps you get Retrieval-Augmented Generation done. We're going to be diving into 7 techniques that can level up your RAG game. And then we'll wrap up by talking about how you can get your app into production and other folks who have got your app into production. So like I said, let's start with Retrieval-Augmented Generation, or RAG. Fundamentally, RAG is a response to a limitation of LLMs. They are trained on mountains of data, but they're not trained on your data. Your data sits behind your firewall where OpenAI can't see it. It's sitting on hard drives or in databases or behind an API. And your data is the most interesting data from your perspective. If you want an LLM to process your data, you have to give it to them. But you can't just give them all of your data at once at the moment, because they simply can't handle it. If you give ChatGPT all of your documents at once, it will barf. Context windows are in the hundreds of thousands of tokens. But you probably have hundreds of millions of tokens of data. Even in a universe where you had LLMs that had infinite context windows, it would still not be practical to give an LLM all of your data every time. You have to be selective, which is where the retrieval part of Retrieval-Augmented Generation comes in. You have to give LLMs the most relevant context. And that's a very complex problem. But there's more to it than just simple context size. There are some unique challenges here. What do we get out of doing RAG? 4 things. First, accuracy. We want the right answer, obviously, but by retrieving the most relevant data and giving it to the LLM at query time, we make sure that the answer is not just correct, but as complete as it can be. Incomplete answers can be just as misleading as answers that are entirely wrong. Closely related to accuracy is what we call faithfulness. Terms differ for this across the industry, but essentially it means no hallucinations. LLMs try very hard to be helpful, too hard sometimes. Giving them the data and only the real data helps prevent them from inventing things in an effort to be helpful. Nobody wants hallucinations. They're one of the most frustrating parts of working with AI. Another big challenge is recency, especially interesting in a timescale database. While you can, to some degree, improve accuracy and faithfulness by fine-tuning a foundational model on your data, doing so is time-consuming and expensive, and your data changes all the time. Sometimes it changes in real time. RAG is the only practical way to keep up with ever-changing data by allowing you to constantly ingest new data. And finally, there's provenance, by which I mean the LLM can say where it got the answer. Being able to cite your sources is good in academia, but when you're talking about search, it's essential. Finding the document that the answer came from is often the point of the search. It's not just a nice to have. That's why we do RAG. How do we do RAG? The core of RAG is retrieval. And there's a bunch of ways to do that at the highest level. You can, for instance, just do keyword search. The same algorithms that we've been using in search engines for years are pretty good at finding information. There's also structured queries. If you have a huge relational database, it doesn't make sense to dump it all to text and give it to an LLM, because you have all of this valuable relational data about how this data relates to the other data in your database. So instead, LLMs are getting pretty good at writing SQL, and you can get the LLM to query your database directly and retrieve context that way. And then there's vector search, which is the one that you hear about most often and the one we're going to be talking about a lot today, partly because it's the new kid on the block, but also because it's really uniquely powerful. For vector search, the first thing you do is convert your data into numbers, specifically gigantic arrays of numbers called vectors. The models that do this work are closely related to LLMs, and they encode your data as meanings rather than as keywords. The total set of available vectors is enormous, and it's known as vector space. Converting text into numbers is therefore known as embedding your text into vector space, And the resulting numbers are just called embeddings for short, which I think is kind of confusing. It's so many degrees of indirection away from what it is that you've actually done. But the effect of embedding all of your data this way is that you can then take your query and embed it into vector space the same way. Because of the way vectors encode meaning, the answer to your query is likely to end up mathematically nearby in vector space to the data that is able to answer that question. And those two things can be located with relatively simple math. So this allows you to do RAG. You embed all of your data, then you embed your query, and you retrieve context that's nearby to your query in vector space. You feed that context and your query to an LLM, and you get a reasonable answer to your query. The LLM is not just regurgitating the context, it contextualizes and explains it as well. You can use this amazing vector search, or you can use keyword search or structured queries, but of course you can do even better and use all three at the same time. Keyword search is going to work really well if you happen to search for the right keyword. Vector search will work even if you use a different keyword, but the meaning is the same. So in practice, you want to do all of them to some degree. So that brings us to LlamaIndex. LlamaIndex is an open source framework that connects your data to LLMs. We're available in Python and TypeScript, and we also have commercial offerings. We have LlamaParse, the very best PDF parser in the world, and LlamaCloud, a service that provides a fully managed service that will ingest, parse, retrieve, and query your data for you. But that is getting ahead of ourselves. Connect your data to LLMs is one of those problems that's easy to say, but very tricky to do in practice. So here's a typical RAG pipeline. You load your data from your sources, and you ingest it and prepare it to be processed. There's a lot of complexity in that. Then comes indexing. You embed your data, preparing it for vector search, which is not the only way, like we said, but it's a great way. Then you put that data in a vector store, and there's all sorts of choices to be made there. And when you're ready to query that data, you first have to retrieve the most relevant context. That's another task with a ton of hidden complexity, often involving post-processing of the retrieved data. Then you have to combine that context with a prompt, and everybody knows that prompting is its own whole art form, but combining a prompt with context can also be a task with hidden complexities. And finally, you get your results, which depending what you're doing, might require further processing, like turning it into valid JSON or something like that. There's a lot going on here. RAG is a magical technology, but magic is tricky to get right. Let's talk about how LlamaIndex gets involved at every stage of this process. Before you get started, you get to pick your LLM. We support dozens of LLM models and more every day via APIs like Ollama and hosted options like BentoML. Let's start with ingestion. The very simplest form of ingestion is just to load a bunch of files on disk into memory directly. In LlamaIndex, you can do that in one line of code. This can handle a huge variety of formats, including CSVs, PDFs, Word files, and also images, audio, and video for when you want to do multimodal things. In a real application, you wouldn't store everything in memory. You'd use a vector store like Timescale. But let's keep going. What if your data isn't in static files? What if it's in Google Drive or Notion or a database of some kind? LlamaIndex also provides a registry called LlamaHub, available at llamaHub.ai. And the hub provides a huge library of software to help make building RAG applications easier. That includes connectors to connect to your favorite data source. That includes tools for building agents, data sets for evaluating your applications, and a set of things that we call llama packs, which are essentially arbitrary code packages, which turn various complicated tasks into one-liners. I'll mention all of these again as they become relevant. If you need to load from some other source, check out LlamaHub, but in this example, we're going to stick with Simple Directory Reader. If you're happy with our defaults, then you're done. You can go to the second line where you index the data by sending it to an embedding model. But you might not be satisfied with the defaults, in which case you would want to build an ingestion pipeline. This lets you configure a series of transformations. You can specify how you want to split your documents up for embedding, which is its own whole topic that we're not going to be going into now. And you can specify what metadata you want and what embedding model to use. The result of this parsing process is that you get a set of nodes which you can then start indexing. And of course, in production, you're probably going to end up running the same pipeline repeatedly as you experiment with these parameters. So we allow you to cache your pipeline and reload it instantly if nothing has changed, only rerunning the parts that have been modified. This brings us to the next stage, which is indexing. As I mentioned, this is the stage where you take your chunks of data and you embed them into vector space. We support a huge set of embedding models, like we support a huge set of everything. And these all have different performance in terms of both speed and quality of retrieval. Your workhorse here is Vector Store Index, which takes care of getting all of the embedding done, whether it's via a remote API or a local model. You'll see us call out to Vector Store Index over and over in these examples coming up. Depending on your use case, you may also want to check out our knowledge graph index. It can take unstructured text and split it into entities and relationships, and then perform entity-based queries on that data. Now you have all of your embeddings, it's time to store them. We support dozens of vector stores. Vector stores are all taking giant piles of numbers and allowing you to search against them using vector math. However, there's a lot of differentiation in the space, as we're going to see later, in which ones allow metadata filtering and hybrid search and other features. Don't worry, I'm going to explain what those things are. Which brings us to the next stage, which is querying, and the thing that we're not going to be talking about very much, which is prompting. Other RAG frameworks talk a lot about prompts and prompt engineering, but we take a different view, which is that we are a batteries included framework, and that means we have come up with excellent prompts. They are tried and tested and finely tuned, and we've built them into the framework so you don't have to figure all of that stuff out yourself. If you want to, of course, you can modify the prompts. This starts with the most basic thing, which is inspect the prompts, so you can see what the defaults are that we provided for you, and you can pass in your own either in advance or at query time. The syntax of prompt customization will be very familiar if you've used any other library to do this stuff before. So now we're at the querying stage. Let's start with the most basic form of querying. We just get our index to give us a query engine. We accept all of the defaults this way, and we just run a query. And then you're done. This is great. It's part of why LlamaIndex is so easy to get started with. You can go end to end, all of those stages of RAG that I was just talking about in 5 lines of code if you really want to. Of course, like everything in LlamaIndex, your query engine can be customized. What we're doing by default is retrieving the 2 most relevant pieces of your data and returning those as the context to your LLM for querying. But in these days of very large context windows LLMs, you might want more than 2 pieces of data. You might think that you can fit 10 or 100. So you can configure your own retriever here and retrieve a different number of pieces of context. You can also configure the synthesizer, that is how the engine puts the query together before it sends it to the LLM. There's a bunch of available strategies here for combining your context and your query, which we don't have time to go through today. But effectively what they all do is group your chunks of context together and then query the LLM with them. Finally, you can create your query engine by combining your retriever and your synthesizer and querying the LLM, just like we did before. So that was basic querying end to end. Now let's look at those advanced strategies that I was talking about. The first one, which we conveniently package up for you, is the sub-question query engine. The problem we're trying to solve here is complicated questions. If you have a lot of unrelated data sources, it may require getting data from more than one of them in order to answer a single question. That is impossible to do with a single query to a single source. So what the engine does is break your query up into a series of simpler questions using the LLM. Then, given an array of data sources, it routes a query to each data source appropriately, and then it gets the answers and combines those answers from each data source into a single answer. In this toy example, we're just creating one data source, but we could create more. We've created a simple query engine, such as we had in the previous slides, and we're assigning metadata to it, which specifies what this tool should be called and roughly what it does. The sub-question query engine looks at each of the smaller questions it has generated and uses these descriptions that these metadata descriptions to decide which source is most likely to be able to answer the question. And you can have as many sources as you want. The next problem we want to tackle is precision. Basic RAG can struggle with making sure that the context is precisely related to the query. And one tactic for handling that is known as small to big retrieval. In small to big, we break a large document up into very small chunks, like single sentences, and we perform retrieval on those very specific sentences for maximum precision. But that sentence by itself, while it's very closely related to your query, it might not be enough context to be able to answer the question. So at the synthesis stage, before we hand the query and the context to the LLM, we go back and we retrieve 5 or 10 sentences of worth of context before and after the sentence we retrieved. And this gives the LLM more context to work with while maintaining the precision that we wanted. Getting this done in LlamaIndex is disarmingly simple because, again, we've done all of the work for you and packaged it up nicely. When creating our query engine, we can supply a list of node post processors which work after retrieval but before synthesis. And we can use the catchily named metadata replacement node postprocessor with a target metadata key of window to automatically search through nodes, which all have links to their previous and next nodes. That's how it knows how to get the context on either side. And it will link together the previous and the next 5 nodes before sending the query to the LLM. Small to big is precision by post-processing nodes, but you can also get better precision by pre-processing them. One way that you can help the LLM out is use existing metadata that you have about your data and filter on that before retrieval. In addition to using embedding retrieval, some vector databases natively support attaching arbitrary metadata to each of your embeddings. Timescale, for instance, supports this. An excellent example of this technique is if you were dealing with documents representing annual legal filings of a company or multiple companies. You could attach the year as metadata and pre-filter on that, or you could attach the company name as metadata and pre-filter on that. Shown here using the exact match filter. Using the vector index auto retriever, we can describe each of the metadata fields and get the LLM itself to decide how to apply metadata queries, allowing you to continue to query in natural language without any manual refinement on your side. So the framework will do this metadata filtering for you. As you can see from this list, most of the vector databases we support also support metadata filtering, and only a handful don't, so that's good news. Our next example is hybrid search. Embedding-based vector retrieval is truly magical, but as an industry, we have poured decades of effort into building search engines, and at this point, they're really pretty good. So some of the most interesting vector databases are actually search engines executing a pivot. They allow you not to do just top K retrieval, but also use existing search algorithms, one of the most prominent of which is called BM25. Once you've got a database that supports hybrid search, using it is extremely easy. You pass vector store query mode equals hybrid, and then a value called alpha. It runs the same query against using both vector and traditional search, and alpha determines the degree to which the search relies on results from traditional search or vector similarity. 0 means entirely use traditional search, and 1 means use entirely vector search. As you can see, the list of vector databases that also support hybrid search is a lot shorter. And then, of course, there's Timescale's specialty, which is time series filtering. We're going to see when we run through the notebook that this can be super useful for time series data in particular. Another use case for advanced retrieval is complex documents. Not every document is just a pile of text. They often contain complex tables. Let's consider how we could break down a complex document into a set of simpler queries. But first, I need to introduce you to our ability to query tables. We have a fantastic built-in called the Pandas query engine, which allows you to create a Pandas table in Python, and using the LLM, it can generate correct Pandas calls that query those tables to get the right values. One of the things that LLMs are not very good at is math, but Pandas is very good at math. So if you want things like sums and averages of large columns of numbers, getting Pandas to do it, controlled by the LLM, is a very good solution. We can then provide a description of each table, and that description can be something that we provided or we got the LLM to derive it. And we can create a series of what are called index nodes. These are just like the regular nodes that we were talking about earlier that you saw me pass to vector store index, but the retriever I'm about to introduce will know to treat them specially. Each index node contains an index to a dictionary that we're creating here. The dictionary consists of instances of Pandas query engines, one for each table in the document. Now for completeness, we'll show parsing the rest of the document, from which you can assume we've already extracted the tables. We create a vector retriever that operates over all of our nodes, both the regular nodes and the index nodes. Now we set up a query engine just like we did earlier. A retriever, a synthesizer, combined into a query engine, but this time we use a recursive retriever. The recursive retriever expects a list of retrievers to use. So we give it the vector retriever we just created, and it also knows that if it retrieves an index node, it should look up the index it finds in that node in the dictionary of subquery engines and perform the query there. So we pass it the map of IDs to query engines that we created before, and we create the query engine. Now a query to the top level engine will result in retrieving all of the relevant nodes. And if one of those nodes is a table, then it will perform a pandas operation on that table to retrieve the exact results before returning that to be synthesized into the prompt to the LLM, which will then return the full answer in context. Another very common advanced retrieval use case is wanting to query a SQL database directly, as I mentioned. There's no end of really great data in SQL databases, so the use case here is obvious. Let's break this down and show how it's done. Under the hood, LlamaIndex is using SQL Alchemy, which if you've ever done data work in Python, you'll already be familiar with. Here we just connect to a database and initialize LlamaIndex's own SQL database class. The SQL database class is handled by the, again, catchily named natural language SQL table query engine, which is another built-in from LlamaIndex. What this does under the hood is pass the schema of the table as part of the query to the LLM and gets it to generate SQL. This is obviously tricky stuff. It works best if you have a powerful LLM like GPT-4 or Claude Opus. But if you know the name of your table in advance and you're sure the schema will fit into your prompt, this is an incredibly simple way to get it done. You can see how this would fit well into the recursive retriever we were looking at too. You could make one of your index nodes be a pointer to a SQL table instead of a pandas table. So what do you do if that's not true? What if your table schema doesn't fit into memory, or you don't know which table to query in advance? In that case, you can create a SQL table node mapping, as we're doing here. You create an index of each of the tables, and you turn that into a retriever, which you then pass to SQL Table Retriever Query Engine, which is yet another amazing built-in. In this case, this will search the index for the most relevant table and then pass that to the natural language table query engine and perform the query as it did before. So if you have even if you have a really big relational database with hundreds of tables in it, you can still expect the LLM to pass in just the schema of the relevant table and the query to be able to run queries on that specific table. How does it know which table to query? It uses the LLM and it looks at table and column names. But if you want to be more helpful, you can manually describe the tables, as shown here, to give it more context on which table is likely to be helpful. The final use case we're going to cover today will also be the most complicated because it's not just a retrieval strategy, it's an example of an agent in LlamaIndex. Our favorite example of this in the wild is our demo application, SEC-Insights.ai. SEC-Insights was initially intended as a demonstration of LlamaIndex, but now it is a fully open source demo application that you can adapt and customize to your own needs. What it does is you give it financial filings documents from one or more companies, and it can compare, contrast, and summarize them to tell you what's in the filings. In the latest Y Combinator batch, there's a company where this is their whole business, but for us, it's just a demo. Our first step to do this is to create a query engine for each of our data sources. Here they are very similar sources. They're just in different directories, but they could be entirely different query engines using any of the strategies that we've already talked about today. Now, because this is an agent, we define tools to give it that it can select from. As we did earlier in our SQL example, we give the tools metadata so the LLM can help decide which tool is going to best answer this question. Now we define our agent, which is surprisingly simple. We give it a nice capable LLM, again, like GPT-4 or Opus, capable of tool use. And in this case, it's OpenAI. And we give it the set of tools we've created. Now the agent, when given a query, will enter a loop where it tries to select the best tool, runs queries over that tool, and continues until it gets an answer. In this contrived example, our query is very simple and our tools are very simple. But remember, you could have made any of the above examples that we talked about into just one of the tools available to the agent. So you could have had one tool that was doing sub-question query engine, another tool doing text to SQL, and a third performing hybrid search. You can get up to some really amazing things by combining all of these strategies. So we've seen how to build some really amazing stuff, which brings us to the final step, which is getting it into production. I hope we have some listeners to the Latent Space podcast here. It is an excellent podcast about the rise of AI engineers and the future of AI generally. And recently, the host Sean described 2024 as the year of LlamaIndex in production, and we completely agree. One great way to get your AI creations out of a notebook and into production is Create Llama. Create Llama is a command line tool loosely based on the Create React app. It's an application generator that creates a ready-to-ship RAG application with a working front-end interface and a back-end in your choice of either serverless TypeScript, Node.js, or Python. Just one command, and you've got a working app that you can customize and ship. It has dozens of options and templates attached, and it's a really great way to accelerate your development and get into production quickly. This is a short list of some companies that already have us in production. It's shorter than we'd like because the truly giant companies that we know are using LlamaIndex are often a little hesitant to say so publicly, but rest assured, there are household names with LlamaIndex in production. As a brief example, take Gunderson Detmer. They are a major law firm dealing with startups, and they have an enormous body of internal data informing their current agreements and the state of the tech world. ChatGD is an internal tool using LlamaIndex that lets their lawyers quickly query all of that data for relevant information so that they can answer client questions more quickly. So let's just briefly recap what we learned today. We talked about what LlamaIndex is. It's an orchestration framework, commercial offerings like LlamaParse and LlamaCloud, but also a hub of tools and connectors, and finally a set of tools for getting into production. We covered the stages of RAG. There's ingestion, indexing, storing, querying, and we did all of that in brief. And we talked about LlamaIndex's support for pipelines and pipeline caching, how indexing works, the set of vector stores available to you, and what features they support. We briefly covered prompting and how you can customize your prompts, and how to create a query engine. Then we went into our examples. We started with naive top-K retrieval. Then we went into sub-question query engine for more complex questions. We talked about post-processing for precision with small to big. We talked about using metadata filtering to increase the precision of queries and how that filtering can be automated by further using the LLM. We covered hybrid search to combine the best of vector retrieval with the best of traditional search techniques. And we talked about the recursive retriever for indexing really complicated documents. Then we briefly dipped into the world of text-to-SQL and multi-document agents and how all of these different techniques can be combined. Now that we've seen all of that, let's dive into our demo notebook. This is a notebook showing how to use LlamaIndex with Timescale. One of the key features, like I mentioned, of Timescale versus other vector stores is its focus on being able to do time series queries. So if you have time series data, in this example, we're going to be using git commit logs, which stretch over an enormous period of time. You can use filtering to filter down to the time period that you care about first before you do vector search. Because the notebook can take a long time to run, I have pre-run this notebook. So forgive me, I'm just going to be showing you what happens after it's run. First, we install our necessary packages, LlamaIndex, Timescale Vector, OpenAI for the LLM. And these things are from LlamaHub, this JSON reader, OpenAI embeddings to embed the data, and of course, Timescale's vector database. Just skip past that section. We'll also need an API key. We'll need the OpenAI API key and your Timescale service URL. Now we're going to download a bunch of commit logs as an example, like I said. And we're going to create a set of functions that extract metadata from these Git logs. The parse data function gets the time of the commit. The create UUID creates a unique identifier for each commit. And then the split name function gets the user's name and email from the commit. We don't really need to go into detail about how these are working. Now we load the data. To do this, like I said, you create a bunch of nodes. So the important thing here is that we are creating a text node. Like I said earlier, you can attach metadata to nodes in LlamaIndex, and that's what's happening here. A commit, an author, and a date are being attached to each node individually. Then for the purposes of the demo, we limited the number of records to 500 just to make things run quickly. Next, once you've got your nodes, you have to embed them, like we said. To do this, we're going to be using OpenAI's embedding service, specifically the text embedding 3 small model. And that's what's happening here. We're passing each node to OpenAI and saying, embed this into vector space, and then attaching that embedding to the node. Now that we've got our nodes and we've got them embedded, we put them into our database. In this case, it's going to be Timescale. This is very simple. You just take your vector store, your Timescale vector store, which you've instantiated here, and you add your nodes to the database. So this is the storing phase in that stages of RAG that we went through earlier. It spits out a list of all of the nodes that it stored. And now we create an index. An index is LlamaIndex's primary thing. It's the way that you access a bunch of index nodes to run queries. Now that we've loaded our documents, we want to specify the time that we are looking at them. You can specify various time deltas. In this case, because it's commit log data, and we know that it's over a relatively short period, we're using a time delta of 7 days to split things up. But if you had data that spanned years, you might want to use a month or years as the delta that you split things up on. Now we're going to run a vector store query using a time filter. First, we're setting up our query engine, and we're running our query using our vector store query, and we're doing a filter here. As you can see, we've got it filtered down to the specific time period that we care about. You can also specify a start date rather than a full window, and that is what's happening here with your start time here. As you can see, it's restricting our results to within the specific window that we said, and then running vector searches over that. And finally, you can provide both a start time and an end time, and the time delta that we were talking about. So again, it's looking within individual weeks and within the start date and the end date that we specified. As I mentioned earlier, you can also do filtering based on other things. You can do filtering based on arbitrary metadata. So one of the things that you might want to do, we have authors attached to all of these nodes, is filter by author. So we're going to say not just commits that are within this particular time frame, but commits that are related to this particular author. And this is how you do that using LlamaIndex's metadata filters, just like we saw in the earlier example. We're saying the key is author, and we're saying the author is 𝗏𝗏𝗏𝗃. And again, here are our results. We're getting within the right time period, and also all of them have the correct author as 𝗏𝗏𝗏𝗃, so we can see his commits specifically. And then you can combine these techniques. So in addition to filtering down to 𝗏𝗏𝗏𝗃, we can do the time search query like this. And that is it. Like I said, it's a pretty simple demo, but I hope it gives you an example of how easy it is to use LlamaIndex to do this kind of sophisticated retrieval to really improve the quality of the querying and the results that you're going to get. And with that, I think I will end my share.
Thank you so much for that, Laurie. That was a really great presentation and really interesting demo. Really appreciate you showcasing Timescale there. We're going to move into the Q&A portion of this presentation. If you haven't already, please put your questions in the Q&A. Just hit the Q&A button in Zoom and ask your question there. Or if you don't have a question, you can upvote questions that you resonate with or want to hear the answers for, and I'll try and prioritize those upvoted questions first. Take a few minutes to do that. In the meantime, we've had a bunch of questions throughout the webinar, so I've grouped them into different topics. So maybe the first one we can start with is a technical question about LlamaIndex and kind of the structure of it. So someone asked, what is a node in LlamaIndex, and how can you think about that in terms of the structure? You mentioned nodes and indexes. So I wonder if you can just explain the difference between those in LlamaIndex, and then we can maybe link to some documentation that explains that.
Absolutely. Very simply, a node is just a block of text. It's just a string to which you can attach metadata. So if you imagine when you are querying a huge corpus of data, you're going to have a lot of different documents, and some of those documents might be very long. So we don't index based on each individual document. We split it up into chunks. That's one of the things that I was mentioning in the parsing stage, is that you split your documents up into smaller chunks so that the vectors that you are embedding are more specific. They're related to just that chunk of that document. And nodes are how we manage that. The nodes are just where we store these chunks of text. So each node specifies which document it came from originally, and the index just contains a huge list of nodes.
Fantastic. The next set of questions about models to use. So you mentioned that, for example, in your presentation, to do things like text to SQL, specific models with kind of more powerful capabilities are best for that. So there were some questions in the chat about using non-OpenAI models to do things. Some folks mentioned that they only see examples with OpenAI. I was wondering if you could give an assessment of what kind of tasks you find best for which model types. Obviously, there's a cost associated for more advanced models. So maybe just a summary of what and your recommendations about which model types to use for which kind of tasks, given the stuff that you mentioned about the different methods of RAG.
That's a great question. For most things, relatively simple models will work. If you want an open source model, things like Mistral or Mixtral, if you've got slightly more hardware, will work very well. If you're doing things like text to SQL specifically, like text to SQL is a very specific case, we've only seen the very largest models do very well at that. So OpenAI, obviously, GPT-4. But if you don't want to use OpenAI, there's Anthropic's Claude Opus. It's an extremely capable model. And we're seeing bigger and bigger open source models get released. Just yesterday, Databricks released a huge open source model called DBRX, which we've yet to put through its paces. So I don't know how good it is at text to SQL, but it's supposed to be specifically very good at code generation. So I'd be interested to see how DBRX performs.
So the summary there is for these advanced reasoning tasks, using more powerful models and spending a bit more is worth it. But for kind of very simple tasks where the RAG does most of the heavy lifting and you just need maybe a summary or something like that, then the smaller models or the cheaper models might be a bit better in those cases.
Absolutely. Our default is still OpenAI 3.5, which is very simple. Sorry, very cheap at this point.
Yeah, and totally. And one thing I always find is that as the costs of these models come down over time, your default will get better and better, where eventually people will be defaulting to GPT-4 once GPT-5 is out or the like. So
Yeah.
closing that question, we had actually one question about kind of models supported in LlamaIndex. Daniel asked, does LlamaIndex support Gemini? I'm not sure if that was covered in the slide, but
I think I possibly didn't list it in that slide. But yes, we support Gemini. We've been supporting Gemini since day one of its release.
fantastic. Okay, so there is Gemini support in LlamaIndex. Thanks, Daniel. The next set of questions we had was about RAG and SQL. There was about 5 questions about this. I'm going to ask that set of questions. Let's start with the one from Louise. So Louise asks, when building a RAG system for SQL, how can I optimize the SQL generation for things like joins between tables besides just embedding the table schemas or passing additional context in the prompt? I know you all have done some work around kind of Postgres text to SQL at LlamaIndex. Wondering how you would advise him for that set of kind of more advanced SQL generation tasks.
The answer is first off, use the most capable model you can possibly get. Joins are tricky even if you're a human. So you want the strongest possible model. But one of the tricks that you can use to get good responses here is you can do prompt engineering. You can say, often you're going to know more about your query than just a blind query, right? You're not just running a query, not knowing anything about it. So in your prompt, you can say something like, you're probably going to need to join the table users with the table payments in order to be able to answer this question. And that is a hint that the LLM will take note of and correctly do it. You can even, and this has had very good results, is you can give it an example query. If you're pretty sure that your question is going to be answered by doing a join between 2 tables, you can give it an example SQL query of joining between those 2 tables and say, run something like this, but specific to my query. The people who are doing text to SQL very seriously give the prompt dozens of examples of queries that it might want to run. And it usually just picks one from that, and that really improves the accuracy of the querying that it does.
Along the similar lines, this time on kind of security. So this is from John McBride. John says, what security steps do you recommend for preventing Mr. Bobby tables? That's a reference to like 𝗥𝗲𝗃 or something like that.
Very familiar with little Bobby tables.
Basically from dropping tables and other kind of security things. Just to finish the question, he says, a read-only user is what I'm guessing. What are your thoughts there?
That is exactly what I was about to say. It's important to remember when you're doing text to SQL that text to SQL is not it's not an application interface. It is a SQL querying interface. It's a SQL querying interface that writes the SQL for you, but it has exactly as much power as writing if you gave the user a box that they could type SQL into. And so you have, from a security perspective, that has to be your model. You're like, if I gave this user a box that they could type arbitrary SQL into, what would they do? Or what could they do? Read-only model is like starter. There's no situation in which you want the LLM to have write access to your database. But there's stuff like table level or even row level security that you can implement at the database level, especially in Postgres, to make sure that the user is only going to be able to query the stuff that they have access to, or that they should have access to.
So the next topic that folks asked about was broadly about knowledge graphs. So there were some questions from Jatin, for example, who asked, how can we leverage knowledge graphs in RAG? And in particular, he asked about the knowledge graph index. And then also, what would these graphs contain? Maybe we could just give a summary of kind of knowledge graphs in RAG and how you can use that in LlamaIndex.
Sure. One of the things that we have discovered about knowledge graphs is that people tend to reach for them too quickly. RAG, just ordinary RAG, where you give a bunch of data about what's going on, a bunch of context about what's going on, and then ask the LLM to make the connections, is very effective. So you should use knowledge graphs when you have an existing high quality graph database. Don't assume that turning your unstructured data into a graph is going to improve the accuracy of your queries. It's not how it works. If you've got a really good knowledge graph already, then that's when you would want to run retrieval based on that knowledge graph. The knowledge graph index is something we're actively working on in LlamaIndex. And when I say actively working on it, my colleague Logan is like typing new things into boxes right now about making knowledge graph index work better.
There's one question from Aditya who asked, and this is about the agents topic that you covered. How do you take care when a custom agent needs input from a user for missing information that can't be provided by the retrieval vector store? Maybe that question, and then also just what you've seen as some issues with agents and RAG very briefly.
One of the ways that you can get the specific thing you're talking about is referred to as human in the loop agents, or human on the loop agents sometimes. One of the things that LlamaIndex provides there is stepwise execution of agents, which allows you to monitor the agent as it's going. So if the agent says, I'm stuck, I need some input, you can, instead of it just spitting out the answer, I couldn't find the answer, you can say, okay, now I'm going to prompt the user, give it some more information, and restart this loop with the extra information. That's a more advanced use case. It's not a built-in, but it's something you can absolutely do.
The next question is about something that you mentioned in your presentation about the post-processing node. I'm not sure if you want to just pull up that slide, but basically it's a question about like, how does that work? The Aditya asked, does it use a knowledge graph to get more context? How does that post-processing node work in LlamaIndex?
There's a lot of ways that we do post-processing. Post-processing can be done either, are we referring to post-processing after retrieval or post-processing after querying? Those are quite different things.
Yeah, maybe you could just touch on both. The Oscar didn't specify, so maybe you can just touch on both and the differences.
So post-processing after retrieval is extremely useful for improving your context. So say you've run a basic query across a basic RAG query across a very large database, and you've retrieved 50 pieces of context. One of the most popular things that you can do with post-processing is called re-ranking, where you give an LLM these 50 pieces of context, and you say, rank these by how relevant they are to the actual question. And it will say, okay, within these 50, here are the top 10 most relevant things. And then you give those 10 things to the LLM again and say, okay, here are the 10 most relevant things. Answer the question about this. That sounds like it should be obvious, right? It sounds like the LLM should be able to, if the LLM can figure out what's most relevant, why can't it figure out what's most relevant when there's 50 things rather than when there's 10? But this technique has been shown again and again to work really well. You basically concentrate the LLM's attention on the 10 most relevant things and then ask it the question, and it does better. Post-processing after the query phase is usually more mechanical. It's you've got an answer and you want this answer in a specific format, like you want it to spit out JSON or some XML, or you want it in the form of an API call. So you take you turn unstructured output, which LLMs often give you, they just give you like a sentence, and you parse it into structured output like JSON or something like that.
I want to point out one question from John McBride. John asks, we're actively using Timescale for time series data and hypertables. but I get confused about how to structure the tables and data. Should the vector embeddings be next to the actual data, or should they be in a totally separate vector table that just has the metadata from the original table, or should they be a foreign key to the other table's members? So I'm going to answer this, and as with most things, the answer is it depends. So often what we find is that if you want to store your vectors in the same table as data that's already inside the database, you can do that. There's actually a tool that we've developed at Timescale called PG Vectorizer that will, on a schedule, automatically vectorize things in a column and add that to your table. What we find is that often if data is like already in a table, you can create a separate table and just have foreign key references to these other tables. It's really flexible. The correct answer is it really depends on your use case. But yeah, it shows that you can actually store metadata and vectors and whatever other kind of data you want in the same table. The embedding is just a column type in Postgres and in Timescale. And so you have that flexibility to choose what works for your particular query requirements. There's no kind of one size fits all there. There's another question about folks had about scoring in RAG. There was two questions about should you use a threshold, and Alvaro asks, for example, should you define a minimum scoring for documents that you would finally pass to the LLM? I was wondering what your opinion is on that and kind of the functionality in LlamaIndex, if there's ability to specify like thresholds of relevance.
You can absolutely, in your retriever, specify thresholds of relevance. I don't think that there is a canonical answer here. It's definitely an it depends. My personal preference is not to set a threshold and to effectively set the threshold using a re-ranker. So you cast a wide net with your initial RAG query and say, give me anything that looks even vaguely relevant. And then you get the re-ranker to say, no, this is the most important thing, rather than getting RAG to decide that, since an LLM is usually more capable of working out what's really relevant.
Just doing a quick time check. Unfortunately, folks, we are at time. There's a lot of questions. Even though we've answered 23 of them, there's still 26 questions open. One of the questions is probably easiest to answer, and that is, where can folks go to learn more about LlamaIndex? I know you guys just released a course with deeplearning.ai as well. So where would you recommend folks go to learn more about LlamaIndex and RAG?
We are extremely active on Twitter. That is an excellent place to go to get all of the latest updates from us. But if you're looking to get started, if you just go to docs.llamaindex.ai, that will be all of the links you need to figure out how to use LlamaIndex.
Fantastic. And sincere apologies, folks. We are out of time, and Laurie is a very busy person, so he has to attend to other things. I just want to give a thank you to everyone for attending. What we'll do is I'm going to save a copy of the questions and put some links in a follow-up email so that you'll have a set of resources. And if you want to watch this again, don't worry, you are going to get the recording. So from us at Timescale and from Laurie, first of all, Laurie, thank you so much for being a fantastic guest presenter today. And thank you everyone for asking great questions and a lively chat. Final reminder, if you want to get 90 days free of Timescale, just go to the link that you see on the screen, tsdb.co/webinar sign up, and have a wonderful rest of your day. And once again, thank you, Laurie, for that great presentation.
Thanks for inviting me.
Take care, everyone. Have a good day.
Bye, everybody.